Welcome to Arid Online Academy. My name is Larry Oguntoye, your chemistry professor. In case you have not subscribed to this channel, quickly click the notification bell and subscribe so that when I drop a video like this, you'll be the first to be notified. Now, in this video, we're going to consider O620 paper 6-1, May, June 2020. So let's kick start. A student investigated the dyes contained in different colored inks using chromatography. Water was the solvent. The diagram shows how the student set up the apparatus. Now, in this particular question, you were asked to identify the possible errors in this setup. And what are the possible errors in this setup? First, check the baseline was drawn in ink. Baselines are supposed to be drawn in pencils. If baselines are drawn in ink, they will dissolve in the solvent and it will be washed off. And also, the spots are below the solvent level. The spots are supposed to be on the baseline, and the baseline itself is above the what? Above the solvent level. Okay, these are the two key, errors in this particular experiment. Now, it says which ink contains the greatest number of soluble dyes. Simply, how do you identify ink that contains the greatest number of soluble dye? You have to count the number of spots that each of the inks was separated into. So you have the black ink here separated into 3 spots, and no other ink was separated into 3 spots. The other level we have is 2 spots and 1 spot. So black ink, okay, is the one separated into 3 spots. So it's the greatest number of soluble dye. 2 inks are made up of single soluble dye. So which of the 2 inks are made up of single soluble dye? Here, just check the one separated into single spot. Yellow was separated into single spot, and blue was also separated into single spot. So blue and yellow will be, the answer to this. You must get both, correctly before you can score the 1 mark there. From the diagram, it is not possible to tell if the red ink contains different dye. Suggest how the experiment could be changed to find out if the red ink contains different dyes. Okay, maybe the reason there was no separation here into spot is because the components of the red ink could not be dissolved by this particular solvent. So we could decide to choose a different solvent to see if the components of the red ink will dissolve in the solvent, and if they dissolve in the solvent, then they will be carried along the absorbent paper. So the answer to that will simply be use a different solvent for the chromatography. Okay, so let's look at question 2. A student investigated the reaction between dilute hydrochloric acid and 2 different aqueous solutions of sodium carbonate solution E and F. So study your experiment properly. When you have 2 or 3 sets of experiment, just find out which variable changed in the experiment. Now, in this particular experiment, a burette was filled with hydrochloric acid. Okay, a measuring cylinder was used to take solution E and poured into the conical flask. Okay, thermophthalate indicator was used here. The diluted hydrochloric acid was titrated against the components of the conical flask, and so we have these results for the burette reading. So the final burette reading, okay, is taken from here. Initial burette reading from here. This is 0.0 and 10.2. You can read this 10.2. Okay, so find the difference in the value, that is 10.2. So how do you know to what decimal place you need to record your burette reading? Just take the example given in this question here, 0.0. So your own burette reading 2 should be to 1 decimal place. Now, experiment 2 was also performed following the same procedure, except for the fact that a different indicator was used, which is methyl orange indicator was used instead of thermophthalate, but the same procedure was performed, and I find out that a different result, was measured. So here, the initial burette reading, you can take your reading here, 5.5. Final burette reading was taken care of here, 25.9. Find the difference between the 2 of them, you have 20.4. Then we have experiment 3 here. Experiment 3 was also performed following the same procedure, but in this case now, a different solution was used. Solution F was used, and methyl orange was used. So in both experiment 2 and experiment 3, methyl orange was used, but different concentration of of sodium carbonate. Solution E was used in experiment 2. Solution F was used in experiment 3. So the only variable we can see here is the concentration of the solution. And of course, the readings are from here. We have the initial burette reading and the final burette reading. Then you find the difference between the two of them, 30.6. Now, what color change was observed in the conical flask in experiment 2? What color change was observed? Okay, basically, here we are talking about experiment 2. What did they use in experiment 2? They used methyl orange in experiment 2. Methyl orange was used in experiment 2. So you know what your methyl orange is in what they call it, in basic environment, okay, and what your methyl orange is in acidic environment or neutral environment, okay. So we have the color changes from yellow, to orange, or yellow to red, okay. Yellow to red, yellow to orange will be appropriate color change. Now, compare the volumes of dilute hydrochloric acid added in experiment 2 and that in experiment 3. We are supposed to compare volumes. All you needed to do is to look at your value. In experiment 3, we have 30.6. In experiment 2, we have 20.4. So compare the readings, okay? Just tell us how much more of hydrochloric acid do we have in experiment 3 than experiment 2. So if you compare 30.6 and 20.4, you find that is about 1.5 times that used in experiment 2. So volume of hydrochloric acid added in experiment 3 is 1.5 times the volume added in experiment 2. Okay, so what reason could that be? Very simple reason. Solution F is more concentrated than solution E. If it is more concentrated than solution E, that simply means you need more volume of acid to neutralize solution F than it is required to neutralize solution E. Now, D, determine the simplest, whole number ratio of dilute hydrochloric acid used in experiment 1 and experiment 2. So in experiment 2, we use 20.4. In experiment 1, we use 10.2. So just do the ratio of the two of them, 20.4 ratio 10.2. That will give you 1:2. Make sure you get your ratio properly. This is experiment 1, this is experiment 2, so that you don't switch it to write 2.1. This will not be correct. Okay, good. So you get your value here. For your reason, you get 1 mark. Okay, for stating the difference in volume, you get 1 mark. And for stating the color changes here, you get 1 mark each for your color changes. Okay, good. So now, what volume of dilute hydrochloric acid will be required in experiment 3 if it was repeated using thymophthalate indicator instead of methyl orange? So look at this. Now we'll find out that between experiment 2 and experiment 3, the experiment 2 and experiment 3, yes. In experiment 2, we use methyl orange was used in experiment 2. In experiment 3, methyl orange was also used, but we'll find out that we have more volume of acid in experiment 3 than in experiment 2. That is as a result of the difference in concentration of solution E and solution F. So that means whenever solution F is used, you have more volume of what? More volume of the acid required. But in this case, now if you repeat this experiment with thymophthalate instead of methyl orange, what do we expect the volume, the volume to be? So let's go and look at an experiment where thymophthalate, was used. That is in experiment 1. In experiment 1, thymophthalate was used in experiment 1, and the value with solution E, and the value gotten was 10.2. Now, if we use the same indicator, thymophthalate, and we change the concentration of solution to solution F, what will be observed? We have found out that between experiment 2 and experiment 3, solution F, increased the volume of acid used by a factor of 1.5. So the same thing here, if we keep the indicator constant and change this type of solution used, we are also going to be introducing a factor of 1.5 into this particular volume. So if in experiment 1, 10.2 was used when solution E was used, now if we repeat this experiment using solution F, what do we expect the volume to be? It's just multiplying your 10.2 by 1.5, and you're going to be getting 15.3. So if experiment 3 was repeated using timophthalate indicator with solution F, the volume of acid expected will be 15.3 cm cube. So to get your mark here, you need to give, value 15.3, and your cm cube will get another value. So you get your 2 marks here. Now, the conical flask was rinsed with dilute, with distilled water between each experiment. Why was the conical flask rinsed? Why do you have to rinse your conical flask within experiment if you are using the same conical flask? Okay, it's basically to clean the flask and remove residue from previous experiment. That is pretty straightforward. Why does it matter if a little distilled water is left in the flask after? Why does it not matter if a little distilled water was left in the flask after it has been rinsed? Your conical flask contain your sodium carbonate, right? And whatever the amount of sodium carbonate in the conical flask, you're going to titrate acid, against it. You're actually titrating your acid against the amount of sodium carbonate in the conical flask, not necessarily against the concentration. It is the amount, okay, that matters. So distilled water does not change the amount of in solution E or solution F present. The amount in moles will not change, but the concentration can change, but the amount in moles will not change. So 25 cm cube of solution was already measured into the conical flask, which contained a particular amount of sodium carbonate. So even if your conical flask contained water to half of it, okay, and you add 25 cm cube of your solution E or solution F, it still does not change the amount of of the volume of acid that will be required to titrate against it. Okay, so you need to have it at the back of your mind. The still water does not change the amount of substance present, it can only change its concentration. Okay, it may be diluted, but the same amount will still be there. Okay, a very simple example is if I have 2 cups, okay, I have 1 cup here filled with water to half, then I have another cup filled with water to the brim. If I put 2 cubes of sugar into these 2 cups, and I ask you which of the 2 cups, A or B, contain more sugar, the answer is pretty obvious. Both of them contain the same amount of sugar, but different concentration of sugar. So this particular question is testing your understanding of this the solution. State 2 sources of experiment in this sources of error in this experiment. For each error suggests an improvement that will reduce the error. If you check in this experiment, okay, measuring cylinder was used, to measure the amount of sodium carbonate put into the conical flask. So an improvement will be using a pipette. Just use a 25 ml pipette to measure measure the amount of sodium carbonate. Okay. Now also there was nowhere that we saw that the experiment was repeated. Okay. There was no first titer, second titer, third titer. Okay, to look for concordant value. So you need to repeat the experiment and find the mean to be able to determine the volume of acid used in the experiment. Okay, that's pretty simple. So let's move on to question 3. This is on qualitative word analysis. 2 solids, solid G and H, were analyzed. Solid G was copper carbonate. You have been told that solid G is copper carbonate. Okay, tests were done on each of them. So let's first look at solid G. Copper carbonate, just have the back of your mind, what are the properties of copper carbonate? Solid G was placed in a boiling tube. Dilute, acid was added to it. Any gas proceed was tested. So if you add acid, to a carbonate, of course, you are going to see effervescence. Okay, salt water and carbon dioxide will be formed. So he said any gas produced was tested. So your observation is the fact that you have effervescence, okay, will occur. Okay, then of course, this is copper plus sulfuric acid. So imagine you having copper and sulfate. Definitely a blue solution will result, because the salt that will be formed will be copper sulfate. Copper sulfate will be formed, and that will give you a blue solution. And of course, how do you test for the gas? Because they also told us that the gas was tested. So since you know that carbon dioxide will produce a carbonate, okay, So the carbonate will produce carbon dioxide. The carbonate will produce carbon dioxide. So how do you test for carbon dioxide? You test carbon dioxide with what? With lime water, and carbon dioxide turns lime water what? Milky. So you scored your 3 points for that. So identify the gas produced. The gas definitely is going to be what? Carbon dioxide. So you can write it in words. If you're writing in the formula, make sure you're sure of the correct formula. Aqueous ammonia was added slowly until in excess to the solution. So basically, we know the solution contains copper ions, right? So something that contains copper ion plus ammonia from your qualitative analysis page, definitely when you first add it, it drops. You're going to get a pale blue precipitate, and the pale blue precipitate dissolve in excess to form a dark blue precipitate. Okay, please, it's very essential that you note that whenever you are asked to describe what happens to a solution when they add in slowly, then in excess. You can see the various steps there. Tell us the color of the precipitate when it was added slowly, that is in drops. Then the color of the precipitate, okay, when it was in excess, or whether the precipitate dissolves or what or not. Those are the things that will earn you your 3 marks. So I'm going to get my pay, blue precipitate, here at first. Then of course that the precipitate dissolve to form a dark blue solution. I will earn my powerful 3 marks there. Now on solution H here, okay, so solution H was tested too. A flame test was carried out, and you have a yellow flame. Okay, so you're already suspecting sodium, okay, as a cation present there. Yellow flame, sodium as the cation present there. Solution H was placed in the boiling tube and was heated strongly. Okay, condensation appeared near the mouth of the boiling tube. You know what this means? That they put the solution in the boiling tube and they heated it. Then they noticed the formation of condensate. Okay, that tells us that possibly this solution contains water of crystallization. Okay, this solid contains water of crystallization, and when it is heated, the water of crystallization turns into vapor. And because the upper part of the tube is cooler compared to the lower part of the tube, the vapor will condense here. That is the formation of condensate. So begin to have that idea at the back of your at the back of your mind. Solution H was dissolved in distilled water. The solution was divided into equal portion. They told us that when they add nitric acid, okay, followed by a few drops of silver nitrate was added to the first portion. He said the solution remains colorless. So if you add silver nitrate to something and it remains colorless, that tells us that we do not have any halides. So no halide is present, no chloride, no iodide, no bromide. If they were present, you are going to have, white precipitate identifying chloride, cream precipitate identifying bromide, and yellow precipitate identifying iodide. So now we have eliminated halides from, this particular, experiment. For this particular solution H. Now let's look at test 4. It says that dilute acid was followed by a few drops of barium nitrate was added, okay, to the solution. So if you add barium nitrate to a solution and you are getting white precipitate, that precipitate may be as a result of your barium sulfate or barium chloride. But since we have said that no halide is present because of our observation and test in test 3, we have nullified this. So possibly we have barium sulfate being formed. That means that sulfate is present in our solid H. And don't forget, in solid H, we already said sodium was present because of the flame test. Now we are finding out that sulfate, is also present. And we also find out that in test 2, we have, water vapor being formed and condensed at the side of the tube. So we combine all these together, we may be having an hydrated solution. H may be a hydrated, solid H may be hydrated, solid. So let's answer the question. What conclusion can be made from the result of the test? Solid H is not a halide. Of course, yes, it's not halide. We found that out. Now, what conclusion can be made about solid H from the test 1, 2, 3? It is hydrated sodium sulfate. So hydrated sodium sulfate. So you're going to get hydrated sodium, and of course your sulfate there. So get your what? Your 3 powerful marks. Okay, very interesting. You see, very interesting. So let's look at the final question, which is question 4. Cobalt, manganese, and nickel are metals. They react with dilute hydrochloric acid to form hydrogen gas. Plan an investigation to find the order of reactivity of the 3 metals. To find the order of reactivity of the 3 metals. Pretty simple. How do you find the order of reactivity? You are given dilute hydrochloric acid. You are given samples of the metal. Okay. So, of course, you know when you react metal with hydrochloric acid, let's just say a metal with hydrochloric acid, you are going to be getting a salt plus what? Plus hydrogen. So, hydrogen will give you effervescence. You find the formation of bubbles, okay, in the test tube. So, how can I measure the rate of this reaction? I mean, if I measure the rate of the reaction, a metal that is the most reactive will have the fastest rate of reaction. That is the theory, the background behind this experiment. So to make you are able to brainstorm that way, you know metal react with acid. So how can I measure the rate of the experiment? Highly reactive metal react vigorously. They will have faster rate of reaction. So just set up your experiment in such a way that you can measure the rate of reaction for each of the metals. Okay, there are various ways or strategies you can use, but now let us focus on this first strategy. Measure 50 cm of 0.1 mole hydrochloric acid into each of the 3 flasks. You must ensure that your experiment is fair, so you need equal concentration of acid and equal volume of acid. Then you add equal mass of each of the metals into each of the test tubes. Okay, so 5 grams of cobalt of the same surface area. So those are the ways to keep your experiment fair. So 5 grams of cobalt of given surface area into 1 flask. Then you start timing the experiment. What do you want to time? You want to time the time it takes for the reaction to stop. That is a way to measure reactivity. The time it takes for the reaction to stop. So record the time it takes for the reaction to stop. Then you repeat the experiment for manganese and for what? And for nickel. For in each case, you are going to use the same mass of metal, the same volume and the same concentration of acid, and of course you ensure that you are using the same surface area. So the metal with the shortest reaction time is the most reactive metal. Okay, so other methods you can use, okay, is highlighted below. It is pretty simple. When you are doing your planning of experiment, okay, make sure that you mention the apparatus that you use, but you don't have to list the apparatus separately. Just mention them in line in your sentences as you go. Try to write in reported speech or use very concise direct speech, and you'll be fine. Okay, so don't forget to click the subscribe button and click the notification icon so that you can get fantastic videos like this whenever I drop them. See you